Hello everyone, welcome to our last packet of the semester. Okay, we do have obviously the exam and the last lab to get through after this, but this is the last packet, so good job getting here. Okay, now what we're going to talk about is something quite different than what we've seen before, which is intermolecular forces. Okay, so how best to explain that? Well, we're going to try and explain the difference between the words inter and intra, okay? So, if we're in class, I'd just run over to the board and I'd draw you a very bad picture, okay? Try and tell me what this is, right? So, okay. If you said the United States, you are correct. That's a very bad picture of the United States. This is us, right? You are here. Okay, over here. So you can tell me what this is. Not to scale, of course. Okay. That's obviously England, all right? So there's London. Now, when you fly from Chicago to London, what terminal do you go out of? You go out of the international, right? So a flight between America, US, and the UK is international. Okay, inter means between. So if you think about these two things as molecules, international, between nations, international flight, intermolecular, bond, a bond that holds two molecules together. Think about it. There is such a thing as a drop of water. Why is that? Because there must be something connecting one water molecule to the other. Okay? So it's something new. It's a kind of a weaker kind of bond we'll talk about. But an intermolecular force is a weak force that holds one molecule to the next. Okay? Otherwise everything would be a gas, wouldn't it? There'd be nothing holding molecules to each other. Inside the molecules, of course, we have those regular chemical bonds which are much stronger. Right? So when you boil water, you don't get a bunch of hydrogen and a bunch of oxygen atoms. You actually get separate molecules which have just been separated. Okay. Now, I don't really have an analogy for flying, but you know, a couple of summers ago, we went down to Mobile, right? Okay. Fly down there. That's within the United States. Okay. So you know, we call it a domestic terminal, but in chemistry terms, that's called an intramolecular bond in terms of a molecule. Okay, so anything that's bound inside is a regular covalent bond or a regular ionic bond. Anything between is inter. Okay, so intra within, inter between. Okay, so let's get us back to our definitions here. So intra, keyword, between molecules. Intermolecular bond or intermolecular forces between molecules. Oh, sorry, I've messed it up. See my mistake? Intra, I've got to get it right. Intra, inside a molecule, so it's actually between atoms inside a molecule. Sorry about that. No, okay. So that might be a regular covalent bond or a polar covalent bond, and they're very strong. Like we mentioned, when you boil water, you don't break those bonds. The hydrogen-oxygen bond is very strong, in the realm of 350 kilojoules per mole. That's kind of a larger number for a bond strength. Okay, so intra, within, so within a molecule, right, but between atoms inside that molecule. Inter, think about it. That's between actual molecules. All right, in a solid or liquid. So what holds an ice cube together? What holds a drop of water together? It's bonds between the molecules in a solid or a liquid. Okay, now as we mentioned, these bonds must be weaker because they break first. So we get, you know, intact molecules of water when we boil it, not atoms of the components. So they, you know, maybe an order of magnitude or two, so you know, 100 times to 10 times smaller. Okay, now as we learned all the way back in week 1, also in the class, the shorter the bond, the stronger, right? Okay, so if we look at a regular covalent or polar covalent bond actually between hydrogen and oxygen and water, it's only 96 picometers, but between molecules it's 3 times bigger. Okay, so a long bond, you know, if you like, you can kind of draw these as kind of blobs. The distance between molecules is much longer than the distance between the atoms inside the molecules. So short distance, strong bond, long distance, weak bond. Okay, so something new, we've not seen these intermolecular forces before. Okay, so something a little different, and they're obviously weaker, quite weak compared to regular covalent bonds. All right, so they come in 3 basic flavors. Okay, so just some recap here. So the intermolecular forces of bonds are what hold molecular materials together when they're gases or liquids. Okay, there must be something holding the particles themselves, the individual molecules together. Okay, it's kind of weak because they're easily broken. So if you think about it, things that are molecular, like nitrogen, for example, it's already broken all its kind of intermolecular forces at room temperature because it's a gas, right? But water, it hasn't, right? So water at room temperature, one water molecule sticking to the next, but I get up to 100 degrees C, I do break that bond. Okay, so we see that kind of relationship between the amount of energy we add, heat, right, and the state. So when we go from, here's a great example, from a solid to a liquid to a gas for water, okay, when we have, it's kind of a nice example, when we have 2 water molecules, they have kind of a pretty strong bond between them, intermolecular force. That's why ice is a rigid solid, right? And if we heat that up enough, if we get to, and I'll do it in Kelvin, okay, 273 Kelvin provides just enough energy to snap that bond. So it's like snapping a twig, and then you're left with the weaker intermolecular force. And at that point, the molecules can tumble over each other. That's a fluid, that's a liquid, okay? And then finally, at 373 Kelvin, when we boil water, we actually snap that last bond and off they fly in different directions as separate molecules. Okay, so the state of matter tells you the strength of the intermolecular force. If it's molecular, if it's a solid, there's quite a strong bond between the molecules. If it's a liquid, it's relaxed. If you like, you've snapped half of that bond and they can tumble over each other, well, still in contact, okay? And finally, a gas, they're free to move wherever they want because there's nothing holding one to the next, there's no bond between them, okay? And if you think about it, the strength of the bond is proportional to the boiling point or the melting point. The higher the boiling point, the higher the melting point, the stronger the bond, okay? So things with stronger intermolecular forces melt or boil at higher temperatures, okay? So water boils at 373 Kelvin, right? Where nitrogen boils at 77 Kelvin. So it's a big difference in the boiling point, a big difference in the intermolecular forces. Okay, so the nature of the forces themselves, kind of weird. Okay, we'll talk about it as we go through here. And the good news is this is mostly descriptive. There's no real math. Okay, so you just basically learn some new and interesting facts along the way here. So there are 3 kinds of bonds which attach one molecule to the next. As we mentioned, compared to regular covalent bonds, they're very, very weak. Okay, so the first one, and this is something all materials have, and we'll talk about why in a second. Now, it depends which book you read. London Dispersion Forces is the most popular name. Sometimes they call it van der Waals forces. I prefer the descriptive name, which we'll use in a moment. But remember, London Dispersion Force and induced, that's the key word, induced dipole-dipole forces are the same thing, okay? Everything has this, so think of it as like an entry-level kind of bonding between molecules. Every molecule has it. It really depends on the size of the molecule. Small molecules have a little bit of this and bigger ones have more. We'll talk about why in a moment. Okay, so everything has that, okay? Depends on size. This one, dipole-dipole, some lucky molecules can do this special kind of intermolecular force. It's much stronger than the entry level, but it's only for polar molecules. We talked a little bit about polar molecules, I think in the last packet or so, okay? But polar molecules can do this, okay? And finally, maybe if you've taken a biology course, you've probably learned about hydrogen bonding. In biology, hydrogen bonding is a special kind of bond, but in chemistry, it's just a really strong dipole-dipole. It's stronger than a dipole-dipole, and it only really happens between certain elements or atoms we find prevalently in organic molecules, right? So it's very popular for nature. That's how basically nature sticks molecules together with hydrogen bonds like DNA and things like that. All right, so we'll talk about that. Weak through strong. Everybody does the first one. and then certain select molecules do the next two stronger types. All right, so let's jump in. Now, London dispersion forces, you can read this at your leisure, okay? But basically it's induced dipole-dipole bonding. Now, let me draw you a picture. If I'm going to try and explain induced dipole-dipole bonding, I'm reminded of 1984, believe it or not. So 1984 in England, American football, you know, regular kind of like, you know, San Francisco 49ers, Chicago Bears football, was actually on Channel 4 in England, which is kind of one of our kind of minor stations, and it was on at 11:30 at night. So I used to stay up real late and I was really interested in this game, right? And it took me forever to learn the rules of American football. It's just, you know, some teenager watching it on late night TV. And luckily we had John Madden, who many of you have probably heard of. And he was really good at explaining things. And the last rule I understood was being induced offside. Now, what the heck's being induced offside? Think about it. Did you ever watch a football game and they'll say, oh, the offense were induced or the defense were induced? It's usually the defense that get induced because the quarterback will do a hard count or twitch or something like that. And the defense think, oh, they're going, right? And they don't go. And they jump offside and then there's a penalty, okay? So induction is making somebody do something without even trying, if that makes any sense, all right? So that's kind of how it works in induced dipole-dipole bonding. So there's the pictures, but I'll just do it kind of as a simpler version right here. And I'll also include this in the note packet when I post it, okay? So imagine, and the last thing to kind of form a liquid is helium, right? It forms a liquid at like 4.2 Kelvin or something, okay? So that means it's got the weakest bond. If we understand the weakest bond, we understand this process, okay? So if I think of helium at maybe 5 Kelvin, right? So it's moving really slowly, so that's important because, you know, low temperature, low speed. So it's moving really slowly. So when these things bump together, they stay kind of a long while in close proximity, okay? But remember, underneath the hood here, this is the 1s orbital, that little sphere. There's 2 electrons in there whizzing around at the speed of light, aren't there? Okay, so they're in there somewhere, right? Now, these electronic motions are completely random. They're completely random, right? So just for a split second, this happens all the time in every atom and every molecule in nature. Just for a split second, let's pretend they move over here, right? So they're gone from there, and now they're over there. Fair enough. What does that mean? It means just for that split second, this side of the molecule is a little bit delta, a little bit minus. And if you think about it, where they're not is a little bit plus. And what we've made is what we call a time-dependent dipole. Now remember when we talked about polar covalent bonds, like for example the OH bond, right? That was a permanent separation of charge because the oxygen stole a little bit more electrons than the hydrogen, right? So the electrons moved off center. Here these are flipping in and out of existence the whole time. It's not a whole charge, it's a partial charge, but they're just coming in and out of existence as these electrons just flip around. So we have this emergence just for a split second of a temporary dipole. Fair enough, right? Now, this is where the induction happens. Now, think about this as the offense and this is the defense, right? So here are these electrons minding their own business, and what do they suddenly see over here? They see this wall of negative charge, right? So are they attracted to that as electrons or repelled? If you said repelled, you're correct. They kind of run away, right? So they go over here as well. So they go from there over there. So then this side's a little bit minus and this side's a little bit plus. That's why it's called induced dipole-dipole bonding, because we made them run over there, right? So we induced them. Now this side's minus and this side plus. Induced dipole-dipole bonding. Now look, this side's plus, this side's minus. It's like a, you know, it's not really a great analogy, but it's like a really, really weak ionic bond, isn't it? Plus attracts minus. So in an induced dipole situation, we have a weak attractive force between the atoms or molecules, if they're molecular, and that sticks them together. Fair enough, right? So if we look at our picture here, that's exactly what the frame is showing us. Okay, it's exactly what the frame is showing us. It's just a nicer picture. All right, so read through this, but I think if you kind of understood my description here, it makes a little bit more sense. All right. Now, if you think about it, only those 2 atoms are bound together right now, aren't they? But what's going to happen? This next one now has a plus and a minus end. It'll induce the next one over, okay? And it spreads like wildfire through the whole system, yeah? So once they start doing this, they all do it. Okay, it's induction through the whole system. You've probably been induced yourself. Have you ever been to a baseball game and it gets super boring, right? And you know, it's the Cubs game, right? Yeah, okay, I got a picture of the Sox, but it's really a kind of a Cubs thing, right? So if you've ever been at a baseball game and it gets kind of boring, what do people do? Well, you got a drunk person sitting next to you who stands up and waves their arms in the air, right? And then the next person standing next to them stands up and waves their arms in the air. It's the wave. So the wave is, as the person next to you does it, you feel compelled to do it, and then the person next to you feels compelled to do it. That's an inductive behavior, right? So that's exactly what's happening in the whole system. Okay. All right. In England, of course, we don't have baseball. We have soccer, and when people get bored at soccer games, they just do extreme violence. That's a joke. Okay. All right. Now, the relative strength of these forces. Turns out that helium has a boiling point of about 4.7 Kelvin, which means it's got the weakest bond. I think neon, and I'll look on the next page and take a peek in a minute. Okay, neon, if I can just look at my notes on the side here. Boiling point at 27 Kelvin. Okay, so because the boiling point's higher, the bonding between the atoms in neon is stronger than helium. That would mean that this induced dipole-dipole bond is stronger. All right, why would that be? Why would the dipole between those two be stronger? Okay, well, what's the difference between helium and neon? Okay, look in the periodic table. Helium has 2 electrons. We saw them. There they are, right? Neon has 10, and it's all about electrons, folks. It's nothing to do with mass, as the book would tell you. Okay, it's actually all to do with electrons. If I have neon, okay, there it is. Here's my neighboring neon. Okay, I have 10 electrons in there, not 2. So let's pretend just for a split second, 2, 3, 4, 5, 6, 7 over there, and 3 over there. 7 and 4, that's a difference of 3. Sorry, it's a difference of 4, right? So 4 minus 4 plus. So that dipole is 4 times stronger because there's 4 times as many electrons different. So I induce an equal and opposite charge over here. All right, so that's what happens in neon. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. Okay, so if you like, I've thrown 4 ropes across there, not 1. Okay, because the charge is 4 times bigger. Why is the charge 4 times bigger? Because I can scare more electrons over. Okay, I can induce more over here. Okay, so that means that's stronger, and that explains totally why neon has a boiling point of 27, stronger bond between the particles, helium 4.6. And it's all about the number of electrons. Okay, so if we just flip over, and this is a very, very subtle and important point. Okay, as we showed you with the picture, the strength of the induced dipole-dipole bond, which is proportional to its boiling point or melting point, scales with the number of electrons. Right, the more electrons I have, the stronger the bond, the stronger the boiling point, or higher the boiling point. Okay, but that's not what it says in the book. It actually says in the book, the strength of the force, the bond, is proportional to the weight of the molecule. The weight of the molecule has nothing to do with it, but they write it in the book anyway. Why? Because if you think about it, every time I have 1 electron, I have 1 proton. Therefore, it's heavier, all right? So heavier atoms, heavier molecules, by definition, have more protons. By definition, have more electrons. So it's proportional. The mass of a molecule is proportional to the number of electrons it has. It's not the reason why it does it, but it's related, okay? But something we can always work out from the formula is molecular weight. So it's actually easier to think about molecular weight than number of electrons, all right? And as you can see down here, I've got the molecular weight and the boiling point, and it does scale. If we do the number of electrons, right? So helium has 2, then we have 10, and then 18, and then krypton's 36. So as the number of electrons goes up, so does the mass, so does the boiling point. Okay, and on a test, you'd just be asked to kind of put things in order of increasing boiling point. Lightest will go first, heaviest will go last. Lightest has the lowest boiling point, heaviest has the highest. Okay, so that's induced dipole-dipole bonding. Remember, everything does that because everything has electrons. The more electrons you have, the higher the bond strength, the higher the boiling point. It takes more energy to snap that bond. All right. Now, this is 99% of it. 99% of it is the number of electrons, or, you know, the molecular weight if we want to do that. But occasionally you'll get a weird question. So here is that weird question. Okay, so turns out that regular pentane, right, which is C12345H12, C5H12 can be either kind of a long thin molecule, or still the same formula, but it's more globular, right? It's more globular. So it can be a round one or a long thin one. Okay, so round one or long thin one. Turns out that the long thin one has a higher boiling point than the round one. They weigh the same. They got exactly the same number of electrons. So why on earth would the round one have weaker bonds than the long thin one? All right. Now, a good way to explain this is like a trip to Navy Pier. All right. You ever been to Navy Pier? Navy Pier is kind of awesome. All right. So if I think about Navy Pier, and I'll kind of draw it on the side over here. Okay. So when you go to Navy Pier, they have boats, yeah? Cruise ships. And they're attached either sideways, or you tell me, which one is it? Or long ways. The boats dock sideways to the pier or point straight out from the pier? Well, they dock sideways, don't they? Why do boats dock sideways to a pier, not long ways on like that? It's because it's more stable. If I throw 3 ropes from the boat to the shore, it's not going to get blown around when the waves come, right? This one just flop around like crazy and bang into stuff. So this is more strongly bound to the shore than this. And that's exactly what we see with long thin molecules, yeah? I have in the long thin molecule, which is right here, I have multiple places where I can induce my dipole, right? Remember, I can have those electrons flopping around. I can throw 3 ropes across because I've got more surface area, right? If I've got this round one, they can only touch into one place, right? So I can throw 1 rope across, okay? So generally speaking, things that weigh pretty close to the same number of electrons, if they have a higher surface area, that's how this works. Higher surface area, essentially more bonds than a low surface area. So 1 bond, weak force, lower boiling point. More bonds, more collective force, higher boiling point. It takes more energy to snap 3 twigs than 1 twig. Okay, so if you ever see that, things that weigh the same, it's all about shape, but that's a very rare question. All right, so that's things without dipoles, all right? We're making a dipole, right? So induced dipole-dipole bonding. Turns out that some very lucky molecules already have a dipole that's there all the time, 24/7. Okay, a classic example, and it's down here, is HCl. So if we think about HCl, well, actually I'll do, well, we did HF already in our previous packet. I'll do HCl. Low electronegativity, high electronegativity, the electrons are pulled that way. So that's a polar covalent bond. If I do like an electron map, there's more electrons over here. There's a minus end, that's a plus end. So we call that a permanent dipole. Molecules with polar covalent bonds typically have, unless they magically cancel through symmetry, right, which is quite rare. Typically anything with a polar covalent bond will have polar covalent bond, a permanent dipole. All right, so a number of molecules have permanent dipoles. So in addition to that entry-level bonding, those electrons flopping around all the time, which, remember, just the number of electrons in there, if they have this permanent dipole, it adds on top, right? So it increases what would normally be the boiling point or the forces between the molecules, all right? Now, I like to call this, just to help you remember, right? I call this the 2 dogs in the park bond, right? So here's an HCl here, right? Here's an HCl here, all right? So that's the minus end and the plus end. So it's like 2 dogs in the park. There's a dog. There's a dog, right? Have you ever seen dogs in the park? How do they greet each other? The north end of this dog is attracted to the south end of this dog. I know, it's silly, right? Okay. But the plus end of this molecule is attracted to the minus end of that one. So that's a permanent plus-minus attraction. Now, if you think about it, you don't see this in the park, but in nature you see strings and strings of atoms, molecules all bound together, right? So the next one down will have a plus and a minus end, right? And they'll make long strings. Now think about a string of spaghetti, right? So if you try and cook the spaghetti and then you try and, when you're about to get it out of the pot, just try and grab one strand and pull it out. Can you ever do that? No, you can't. You actually pull out a big clump of spaghetti, don't you? Why? Because all the strings are tangled up, and that's exactly what happens in these, you know, these liquids or solids which are made from polar molecules, right? They all make these long strings, and the strings get tangled up. Everything's stuck to everything else at that point. It's a liquid or a solid. Okay, so that's how permanent, we call it, permanent dipole-dipole bonding works. It's on top of the induced dipole-dipole bonding. Okay, so classic examples, anything with a dipole will do this. Okay, so here's, you know, and it kind of depends on the symmetry of the molecule a little bit. This one, it's interesting. I have a C-Cl bond and then 3 CH bonds, right? So that's the polar bond. So this molecule will have, that's the minus, that's the plus, will have a dipole going through its symmetric center. Okay, so you'll see something similar to this when we look at, you know, dry cleaning fluid, for example. Dry cleaning fluid doesn't use water, of course, and water works, and we'll talk more about water in a little bit. Water works as a solvent because it's very polar. So you can do dry cleaning without water by using a solvent that's also polar. So that smell in the dry cleaners is probably some kind of chlorocarbon molecule like that. Okay, so if it's got a permanent dipole, you can just check, you know, does it have a polar covalent bond, yes or no? If it has a polar covalent bond, it has a permanent dipole. It has a higher boiling point than you would expect. Okay, now as for the magnitude of that boiling point, right, or that force between the molecules, it's just like the helium-neon example. The bigger the dipole, the stronger the bond, right? Okay, so here, if we look at this table, we have things on purpose kind of weigh the same. They all weigh around 41, 44, something like that, right? But they have different atoms inside them. Okay, now it turns out hydrogen carbon, the electronegativity difference between hydrogen and carbon is very small, right? So if we look at the dipole in that bond, it's virtually zero. Okay, so there's no extra there's no extra permanent, I should say, dipole-dipole bonding on top. Induced dipole bonding is the same, right? But permanent, there's none here. When we look at this bond, so this has got a CH, doesn't have any charge separation. This has a C double bond O in it, right? And that's quite a big separation of charge, and we can measure the magnitude of that charge separation with this, what's called the dipole moment. It's how strong that dipole is. So pretty strong, so that will form, you know, a stronger permanent dipole to its neighbor. We see a higher boiling point. Okay, so the dipole moment is scaling with boiling point. Stronger bond, stronger dipole moment, higher boiling point. Finally, CN's kind of weird. It's a triple bond. That's like super minus and super plus. So that's even stronger. Dipole moment stronger, bigger separation of charge, higher boiling point. So when you see things of a similar weight but with different atoms inside, it's not about the number of electrons because it's similar. It's about the strength of the permanent dipole. Okay, and the strength of the dipole scales with boiling point. So you may be asked to kind of rank things in order of increasing boiling point given some relative dipoles and similar masses. Okay, so just about to run out of time. We'll save this one for the next video, and that'll be our last video of the semester for new material. Okay, so I'll stop there. See you guys in a minute.